trying to win the competition, because this was always my goal, to win the competition that I'm taking part in. So and I managed to win 2 competitions and be in the money in 6 of them. So I think I was doing pretty okay in those competitions. So in 2018, I co-founded logic.ai, which is a company that does consulting, and also as part of our mission, we are organizing Kaggle Days events. Basically, we founded the Kaggle Days initiative and kind of brought it up to Kaggle to organize, and they let us organize it from the beginning. Also, in 2019, we started as a team, as a company. We started in a competition called Rex's Challenge, and we've won this competition. So since then, I'm working on recommendation engines because I think it's very interesting. Yeah, and we decided also as a company to build our own system for recommendations engines for e-commerce, because it's, as I have said, I believe that it's very useful. And we like to develop these things, and we are writing right now in Rust, our solution, and in Python. And we are recruiting also, so if you want, you can send us an email. Okay, so back to the topic of our today's presentation. I think that recommendation systems are something that is closer to data scientists. Maybe not obvious, but it's still very close. And in the recommendation engines, we have 2 basic types of algorithms, which I will explain in a moment. These are algorithms that are based on collaborative filtering and also content-based filtering. Also, there are many others, of course, types of systems, but we won't talk much about them today. Okay, so as I have said, recommendation engines are not something that is likely to being brought up in the discussion about data science like from the start, but it's very common use case for machine learning algorithms, especially content-based recommendation systems. And already, if you know classification, regression, nearest neighbors algorithms, you can do very much in this area. So if you know these algorithms, if you don't have basic knowledge, you are well equipped to do recommendation systems. This is my opinion, and I think it's true. So the first type of the algorithm that I want to show you is collaborative filtering type of algorithm. And this is something that you would find very intuitive, because it's something that is relying on the fact that if we have, for example, 2 people in the crowd, and if they like one movie, one particular movie, then this relation that they like this movie makes me think, and makes other think also, that if this another person likes other movie and we are so similar, then I will like also the other movie that the person likes. So it's like a transitive relationship. If I like something and you like something, then we are supposed to like the similar things, so we can recommend each other books or movies. So, and this is like a visualization of this. So normally in recommendation systems and in this collaborative filtering, we work with matrices. So we work with a matrix that has, for example, users in rows, and items like movies or books or other e-commerce items, for example, are in columns. So this is in our, later on we have an example, and basically I will try to show you in a real example how it works. So the advantages of this type of recommendation systems is that it's relatively easy to calculate, even with a basic machine learning packages like scikit-learn. It's possible to calculate something like this, and as a byproduct of this algorithm, we get some vectors. If you know deep learning, for example, these vectors are called embeddings. So these embeddings can be used to calculate the similarity between the products, and it's very useful for making recommendations. And another advantage is they give relatively good results out of the box, and I will show you also this an example. So the disadvantages of this type of systems is that when you are using this plain algorithm, it doesn't take into account the attributes of items. So it doesn't take into account the price, the description, the category of the product. It's something that you must think about how to do it. But in the plain implementation, it doesn't just work out of the box. Also, there is a problem with the cold start. If the user just starts on your website, you don't know anything about the user, and this is the problem that is called cold start, then you don't know really what to recommend to the user. That's why sometimes when you're starting to use some service, they ask you to provide basic information about your taste. Like if you register to Netflix, they want you to select a few movies that you like so they can start up the recommendation system. Because this is the only way basically to start. And also from implementation side of view, you need a large number of examples to train such a system. Like think about hundreds of thousands or millions of ratings. Of course, it depends on the number of users and items, but it's still something that you need a lot of observation. And also another disadvantage is that it doesn't work for new users and items. In order to prepare recommendations for new users or items, you need to recalculate it everything. Okay, so this is one thing. Okay, so how this algorithms work is, again, you have a matrix of ratings, and in the rows there are users, and in the columns there are books, movies, or whatever you want to recommend. And this representation that it's a matrix already has very interesting properties, because collaborative filtering works by separating this rating matrix into two matrices, which are for the user and for the items. And by multiplying each vector together, you should get the rating. This is like a linear algebra type of algorithm, and it lets you kind of separate two types of spaces, for the users and for the items. And this is called though this vector is called, and it's a latent space. And in practice, it works like this: that you can represent user and some item like book in this example as a series of vectors. As a series of numbers, and these numbers are abstract, but still you can try to find the meaning of those items. Those numbers. For example, if I train this system and I specify that I want to represent each user and item by 3 numbers. It's a very low number, 3, but I chose it to explain it. So one number can mean that for the user, it means how likely the user can like comedies, for example, or horrors or fantasy books. And this is of course not in the real world. It's not so easy to explain, but just for the presentation, I can simplify this. So I can say that these 3 numbers represent the comedies, horrors, and fantasy. And what is nice about these vectors is that they mean the same thing both for the user and for the book. So the first number, for example, for the book could mean that how much this book is a comedy, or a horror, or a fantasy book. And by multiplying these vectors together, by multiplying using dot product, you get the rating. And when you think about it, it's very elegant and kind of amazing that it works like this. And as I have said, it works by separating this rating matrix into 3 matrices, but you are only interested in 2 of them: the user matrix and the item matrix. Okay, so also similar ideas exist when you want to implement them using deep learning. Deep learning is kind of more advanced way to calculate the same thing, as user and items vectors. And basically, I won't go too much into details about how these algorithms work using deep learning, but you can easily find like information on the web. Basically, it works the same way. You represent users by some neural network embedding and items the same way. And when you want to predict something, you basically multiply the user vector by the item vector. And this is also how you train the system. It's also very elegant way. And deep learning and neural networks, because they are so closely related to linear algebra, means that it's very easy to train even if you have very deep network. And these algorithms are used very widely in recommendation systems also. So it's something that is very interesting, because recommendations engines are not something that is related only to the simpler algorithm, but also the newest ones like deep learning can be used in this area as well. Okay, so another type of algorithm that is very, very useful is called content-based filtering. And basically what the name suggests is that when recommending the items, we're likely to use the content of the item we want to recommend. So if I'm, as a user, looks at some item A, then a website that makes recommendations can use this information. And the next time when I visit the website, they can show me similar items to A. And how to calculate the similarity is the most important thing in this strategy, because basically on this depends the quality of your recommendations. And there are many ways how to calculate similarity. If this is a book or some e-commerce product, maybe we can take a look at text similarity. So how the descriptions of the item is similar, or if it's like a fashion product, like a blouse or t-shirt, we can look at visual similarity, which is probably more important than the description. So these systems are very widely used in practice, because you don't need to do many calculations in real time. What you need to do in offline matter is to calculate the similarity of products. And how it's done in practice, it's like by pre-calculating similarity for items. So for each item that I have in the catalog, I calculate, for example, 20 similar items to this item, and then I can serve those similar items in real time to the users. So that's why it's so widely used in practice, because you can make most of the calculations, for example, at night, and then during the day when real users come to the website, you can just use this similarity between the products to recommend things to them. Okay, so going back to the Kaggle and competitions, unfortunately there are not many competitions that are strictly connected with recommendation systems on Kaggle, but from time to time it happens that there is some competition like this. And one of the examples of the competition that was likely to be used in the recommendation systems, it was the Quora system to decide whether two questions are similar or not. So the training data was composed like this, that they provided in the training data set two data sets basically. One data set were questions with the same intent. So you had basically a set of questions that were worded differently, but meant the same thing eventually. And this is something that maybe users decided. So they need to spend time to label this data set, to take a sample of two questions, and basically a human had to decide whether they represent the same intent or not. And once you have this data set like this, then you can train very easily many text classification algorithms, because you get basically two columns in the data, you get column 1, which is the first question, column 2, which is the second question, and third column is whether these two questions are similar or not. And believe me or not, I think that Quora has one of the better algorithms to recommend things to the user, because every time I go to Quora and I browse some questions, on the next day they are recommending me similar questions, and they are on the point. I can say that I very often use their recommendations. So this is something that you can check it out after the presentation. It was a very interesting competition. I personally didn't take part in this, but I think it was very interesting. Okay, so going next. Also, if you like deep learning, you probably are using these algorithms for image classification or image segmentation. And out of the box, these deep learning models, we took in our project, we took a VGG16 model from Keras. It was pre-calculated already, and we calculated embeddings for items. So we took one of the layers near the end of the network, and used those representations, those numbers, those embeddings, as a way to calculate similarity of items. And you can already see this is an example of, I think it's phone holder for your car. And you can see already that this kind of, these recommendations make sense. They all almost, I don't know what this item is, but all other items are phone holders, surely. It's something they can look a little bit different, like they can have different colors, but they have the same purpose. They hold your phone in car. So this type of recommendations and embeddings can be used where recommendations is more like a visual thing, in fashion, in furniture, for example. And I believe that deep learning is a very good use case for this type of similarities. Okay, so also in recommendation systems, there is one big separation between the strategies that you can use. So most recommendation systems rely on offline strategies. It means that in order to recommend something to the users, you need to prepare similarities of products or those visual embeddings, like I have shown before, like before you recommend something. And this is, of course, this is a very good idea to pre-calculate it as much as possible to the user, because it makes the recommendations done in real time more easy. Because you can basically suggest to the user similar items in real time to the ones that he looked at or added to cart. And this can be already a very good recommendation systems. What you need to do is just track the items that the user looked at or he added to cart, and then when you want to recommend something to the user, you just recommend him similar items to the ones that he looked at or added to cart. Yeah, but this kind of systems have also their disadvantages, and most serious disadvantages of those offline systems is that they don't take into account the context of the user. They take into account similarity of the item, but for example, if the user is in some mood that he wants to find a product, for example, that is a lower price. So if the only thing about the user you know from the context is that he searched for some items and that he sorted by the lowest price, then you have some additional information about the user that you want to use to make recommendations. For example, if the user searched for lower priced items, you don't want to recommend something that is very expensive to him. So this is again, this is additional information that you can use and should use in order to give him a good recommendation. And what I think about recommendation systems, that when you do them, they are very satisfying, because I believe that you are helping the users to find better and more relevant things for them. For example, if even if you reduce the time to find the item they are looking for, it's already something that is very useful for websites and e-commerce websites or other websites, because you are kind of helping the users to save time also by making good recommendations. And you can believe me or not, but I think this area is very satisfying for me personally, and I hope that you find it interesting too and find it satisfying too. Okay, so I'm aware that this maybe is a lot of information for one presentation, but I wanted to give you as much knowledge as possible. And later on, of course, I will share this presentation so you can review it. And another way to deal with recommendation systems, and specifically those more complex ones, is to divide the work into two phases. And what are those two phases is that normally when we're making recommendations, we think about two things. First thing is to generate candidates, candidate items for the user. And this, for example, if I want to show 10 items to the user, I need to have like 100 candidates first. And what these candidates are is just a good items that these are items that come from some strategies that you decided before. And it's kind of an art to make those candidates at first, because what you want to rely on, for example, is the different types of similarity. For example, if you have some item you want to, as candidate items for recommendation, you can think about text similarity, visual similarity. Also, you can think about very simple strategies like co-occurrence of items. And co-occurrence means that if I saw in the past that many items were bought together or seen together in the same session, that it means that they are probably somehow related to the user. If users, for example, buy laptops and computer mouse together, then I can see it from the data, because I saw that in the same transaction, the same cart, they bought laptops and mouse together. So next recommendation can be based on this relation. So for every laptop, I'm suggesting also mouse as an addition. So when you have like those candidates ready, then the next phase is to score those candidates for the user. And while this first stage doesn't have to use very sophisticated algorithm like classification and regression, the second one is, so you care about precision on the stage, and you want to reduce the number of items by making a precise model that is basically deciding whether this item is good or not for the user. And these models, what is important to them, because they are so general, you can use context in those models also. So this type of models can utilize the fact that what I underlined before. If the user searched for some lower placed items, you can create a feature like this. You can create this context, and when you are scoring those candidates for the user, you can take into account this information that the last search of the user was sorted by the price. So he wants to find lower priced items, and the price attribute of the item can be something that is very important to the user. And this is this fact can be used as a feature in those models that rank the items. So to sum up, you can also look it up. after the presentation, but I can assure you that the way how those recommendations are done right now is in two phases. First phase is generating candidates, and in this phase the recall is important. And the second phase is ranking, and in this phase the precision is more important. So you want to use those two strategies together. And why you are not ranking all the products is because it just takes time. It's nothing more, because if you wanted to rank every product in the catalog every time the user visits the website, it would take too much time. Some websites have thousands or hundreds of thousands of products on their websites, and they cannot do it in real time. Okay, so let's go. I prepared some example for you. It's a Jupyter notebook. I'll give you some time to copy the link, and you can follow this notebook with me. This is a GitHub repository, and with one notebook inside, so you kind of can't miss the notebook. So I'll give you maybe 10 seconds more to copy the link, and then I'll jump straight into the notebook. Okay, so I think if you wanted to open this link, you managed to do so, and I will just move and switch to this link. So as I have said, this link is the GitHub repository, and in this GitHub repository, once you clone it, there is one notebook. It's called Kaggle Days Recommendation Systems and Ulaanbaatar Meetup. So this notebook explains a concept of collaborative filtering. I think it's very easy to follow, and I hope that you find it interesting. The data set that I'm using here is from a research group called Group Lens. And this Group Lens research group produces very known data sets for recommendation systems, and especially they provide recommendations for movies. So they have a website about movies. It's not very good-looking website, I can say this, but they have a lot of movies, they have ratings of the movies, they have some descriptions, and they have much data about recommendation systems. And last year, in December, they released a data set that has 25 million ratings from 162,000 of users and about 62,000 of movies. So it's not the biggest data set for recommendation systems, but it's already something that you can use to learn and also maybe to train some interesting algorithms. So I can jump to the notebook right now. The first cell just downloads the data set and unzips it in some folder. I can just follow along. So I'm importing some libraries. Today we'll be using Pandas library, SciPy library to deal with a matrix, with sparse matrices. This package is, if you are dealing with large matrices, this package is a must to use. So I hope that you know it, or maybe you can learn today. And another algorithm that we want to use is Svd algorithm. This is the algorithm that I was talking about before in our presentation, right about here. This is the algorithm that decomposes this rating matrix into two matrices. One matrix is about the users, and the second one is about the items. So we'll train this algorithm, this Svd algorithm, to get the information about the items, not the users. We want to utilize the items matrix. So yeah, so let me just, I already downloaded the data, so I don't want to download it again. I wanted to first show you what's inside the data set. Okay, so once the data is loaded, there are two data frames inside. First, maybe I'll make it bigger. I think this is better. The first data set, called ratings, has 4 columns. First column is the user ID, and second column is movie ID, third column is rating, so whether the user liked the movie or not. And the fourth one is timestamp. We won't use timestamp today. I even removed this timestamp because there are some duplicates. Because one user can rate the same movie many times, we want to remove those duplicates from the data, because it kind of doesn't make sense to, and it cannot be used in this matrix. We can have only one entry, one user and a movie pair. And the second data set here, data frame, is called movies. And what is this? Is just it explaining what the ID of the movie is. So you can look up by title or by the genre of the movie. It's whether it's comedy, romance, and so on. So we'll first think because I prepared this yesterday, the first thing I wanted to check if this algorithm can recommend me similar items to one of my favorite movie series. It's about Indiana Jones, and already I can see that there are 4 Indiana Jones movies here and 1 series here. So we can, later on, I will try to find the similar movies to one of the Indiana Jones movies. Also, there is, I don't know if you know this comedy, it's called Naked Gun. It's a very, I think it's from the 80s. It's a very funny comedy with Leslie Nielsen. And we'll try to find also similar movies to this comedy. So going to the next cell, it calculates the number of unique items and users and movies. It takes a little bit of time because it's 25 million ratings. It's not a small data set. If you have problems with memory on your laptop and you still want to use this data set, you can sample the ratings. For example, you can sample 1 million ratings from this data frame like this. And this you can do if you have troubles with the memory in your laptop and still want to follow this tutorial. Okay, so what we know about the dataset is that they have 162,000 of unique users, close to 60,000 items, so movies in this case, and 10 different ratings for each entry in the matrix. So to use this SVD algorithm, first thing that we must do is to convert this data frame with ratings to a matrix. And what the easiest way, definitely easiest way, is to use a sparse matrix called coordinate matrix. And how it works is just that you build the matrix by providing the coordinates of the entries. Like you can think about two-dimensional coordinates like x and y coordinates. And these xy coordinates are basically the IDs of the user and movie, because these IDs are numbers that can basically mean that if the ID of the movie is 1000 and something, then the same ID can work as a column index from this matrix. So the ratings about the movie Indiana Jones will be in this column index. So we can use those IDs as rows and columns. Okay, so let me just do this. It's very quick. And what it does is sparse matrices are very widely used in recommendation systems. because you wouldn't be able to store all the entries of this matrix in a dense matrix, like a NumPy array. For example, if we were to calculate how much space it would take, so if you had like this number of users, and I think it should be 60,000 users, then you have you have 9 billion entries in this matrix, and this is something that is too much for any computer to handle. So that's why in this area we are using sparse matrices. Sparse matrices don't store zeros in the matrices, because zeros for recommendation systems don't mean anything. They mean that there is no rating for the user and movie. So we don't want to store them. And you can see that we have the sparse matrix. It has only 25 million stored elements. So it doesn't store zeros. So in order to train our Svd algorithm, it's just like 2 lines of code. It calculates rather quickly. In probably like 20 or 30 seconds, I will have these results. No, maybe it takes a little bit more time. Yeah, but yeah, it's calculated. It took about 30 seconds to calculate it. It's a very fast algorithm, and because it's impressive, because we have 25 million ratings, and this algorithm decomposed this matrix into users and items matrices. And we can check out. This is this Svd components has this matrix with movies, and what this matrix with movies means here. The number 200,000 is because the IDs go from 0 probably to 200,000. It should be, in theory, it should be this number, 60,000, but because the IDs of the movies are not one by one, it just created more entries in the matrix that we need. But it's still okay. We can still find the useful numbers here. So, for example, if I take the ID of the movie Indiana Jones, Raiders of the Lost Ark, this is the ID of the movie that I've looked before, right? This is the same ID as here. So you can find any movie in the dataset, check its index, and then check this entry in the matrix. So what it means that it's amazing how it works, because it transforms the information about the movies and users into a series of numbers. So what you can see maybe doesn't mean anything to us, but it means something when you want to compare movies together, because the way how you find similar movies is by comparing this vector of numbers to other vectors in the same data set. It's really something amazing. Maybe if you wanted to try, maybe each of these number means different thing to us as humans. So it also would be kind of interesting exercise to know and try to name what this number means. It can be hard because it can be a combination of several things, but I think it can be done also. So each of these numbers can represent this. For example, if I see a large number like this one, it can represent that this is adventure type of feature of this movie, because Indiana Jones is an adventure movie. So this number can mean that there is a lot of adventure in this movie. Of course, this is like this can be not true, but it's just an example of how you can interpret those numbers. So the next step when you have these embeddings is to train and index a nearest neighbor algorithms. What it does is basically you want to, for every entry in the matrix like this, you want to find similar entries. And this one I won't run in the real time because it takes, I think, 2 or 3 minutes to calculate it. It's not something that is terribly slow, but I don't want to waste your time. I have this notebook pre-calculated before the presentation, so I have already trained this embeddings. And when we have those this nearest neighbors algorithm trained, we can already find that we can find similar movies to Indiana Jones. And you can see here that it's very, very good. Even with the simplest algorithm, this SVD algorithm, it produced a very meaningful results. When we see the results, similar movies to Indiana Jones, we can see that, of course, the same movie is at the top. It's the same one. So it's something that is obvious when you think about this. It's basically means that the algorithm found the same movie in the data set. But the other movies make sense as well. Like the first recommendation would be Star Wars. The second recommendation is the same series, so it's Indiana Jones, part 3 in this case. And then next recommendations make sense for me because when I like Indiana Jones, I like also those movies, and it's very, very true. I like this movie. This is with Bruce Willis, Die Hard, Aliens movies. Monty Python maybe is slightly different type of the movie, but still I like it. Yeah, so you can think that these recommendations make sense. And if we try to find recommendations for the second movie, we tried to check out. It was the Naked Gun. It's a very funny comedy. Then those recommendations also make sense because the first recommendations are the same movie, and I can see most of those movies are comedies, and even the comedies, those are the same comedies and even the same style of comedy. For example, this movie Top Secret is exactly the same style of comedy as Naked Gun. It's like this kind of strange sense of humor that is like maybe not slapstick, but it's like absurd type of humor. And this is very true for this movie, and maybe for this movie, and basically those recommendations make sense even in the simplest type of implementation. So if you want, you can also follow this kind of tutorial after the presentation. There is like a couple of exercises that you can do. First exercise would be, of course, to find your favorite movie in the data set and check if the algorithm works as expected. So this you can use as your personal movie recommender system. So check if you find your favorite movie, does the similar movies make sense for you? Also, another thing is about the algorithm itself. You can check if the number of components of the SVD algorithm can give you more precise results or less precise results. Because remember that even though we are representing the movie as 20 numbers here, it still gives us kind of relevant results. So I imagine that if we used more than 20, the results can be even better than this. But it's something that you can try on your own. Also, SVD is not the only algorithm that can be used for recommendation systems and for decomposing this ratings matrix. There are algorithms like non-negative matrix factorization in scikit-learn and many others that you can try. Also, as a kind of fun way to visualize the movies, you can try to reduce the number of components to 2, and you can then plot the movies on like two-dimensional plot. And if you mark, for example, movie genres as colors, then you can check if the genres of the movies make some clusters together, because what I suspect will happen is that if similar movies are close to each other, because those vectors are close to each other, and this means that these movies are similar, that it must mean that when you plot it in 2 dimensions, similar movies will be close together. So it's also a very good way to visualize the results, maybe as kind of a graph. So yes, so this is this. I hope you liked it. We can go back to the presentation. So to sum up today's presentation, I think that recommender systems, it's not something that should be foreign to data scientists. I think that every data scientist should at least know how to make basic recommendation systems. In fact, as I have shown you today, you don't need a lot of algorithms to make our recommendation systems. You need basically 2 algorithms. First is SVD type of algorithm to decompose the ratings. And second one is nearest neighbors algorithm. And of course, if you want to go with more sophisticated algorithms, you can try. But still, with those 2 or 3 basic ones, you can get very far in this area. So, any questions?